morning, everyone. Spotlight Lecture Series presented by MTX Incorporated has been bringing the best speakers around the world in front of you, keeping up with the motive to inspire, excite, and motivate the Shaastra community. On AMD Day 2 of Shaastra 2022, we have with us one of the most prominent speakers in our lineup this year, Dr. David A. Patterson, renowned computer scientist, Vice Chairperson of the RISC-V Foundation, and the 2017 Turing Awardee. Dr. David A. Patterson, an American computer pioneer and academic, is known for his pioneering contributions to reduced instruction set computer design, having coined the term RISC, and for leading the Berkeley RISC project. He is also noted for leading the research on redundant arrays of inexpensive disks storage with a fellow researcher. He currently is the vice chair of the board of directors of the RISC-V Foundation and the Pardee Professor of Computer Science, Emeritus at UC Berkeley. His books on computer architecture, co-authored with Dr. John L. Hennessy, are widely used in computer science education. Dr. Hennessy and Dr. Patterson won the 2017 Turing Award for their work in developing RISC. We are extremely honored to have you with us, sir.
Well, thank you.
Yes, sir. So now we'll be moving on to the fireside chat. We'll be asking a few questions for which Dr. Patterson will be answering us. So for the first question of the day, when did you decide to pursue an academic research career in computer architecture? Did some particular incident lead to the decision?
Yeah, I was a graduate student at UCLA. I was the first of my family to go to college, so my goal was to get a bachelor's degree. But then this is actually slightly before computer science was you could do a major in it as an undergraduate. But I was a math major, and a math class was canceled, so I took a computer science course, and I fell in love with it. So I took as many computer science classes as I could, even though there wasn't an undergraduate degree. At the end of one of the courses, I kind of casually said to Professor, boy, I sure like this stuff, because I was working my way through college, and I'd sure rather do computer stuff than working in a factory where I was to support myself and my wife. And he, on his own, went and got me a job as an undergraduate, and so that got me interested in potentially going to grad school to get a master's degree. And my wife said, yeah, that sounds, if you can do that, great. And then everybody in my office was getting their PhD. So then I brought that up to my wife, and she said, sure, if you can do it, go ahead. A few years into my graduate school career, I took, a variety of courses, hardware and software courses, but I'd say I was more software oriented. But then our research grant ended, so I needed to get a job, and I ended up working for a local aerospace company. And they were building computers to go on airplanes. And so I'd taken hardware courses, but it wasn't my specialty. But to support myself in graduate school, I started working for building computers. And so I was kind of hands-on building computers there. And when I graduated, my dissertation project was kind of halfway between hardware and software. And so I applied for jobs both in industry and academia. And fortunately, Berkeley was interested, and they really wanted somebody to do hardware. Well, I had practical experience in hardware, and if they wanted me to do hardware, I'd be happy to work on that. So that's kind of how I ended up in computer architecture, kind of a circuitous route.
It is indeed a remarkable journey you have embarked upon. Moving on to the next question. As pioneers in computer architecture, you and Dr. Hennessy, whom we had with us last year for Shaastra 2021, contributed to the RISC architecture through the Berkeley RISC and Stanford MIPS projects. One key difference among these ideas was of register windowing that was adopted in the Berkeley project. Could you explain a bit more about this?
Yeah, so one of the keys for RISC architectures is trying to keep the operands in registers. So kind of the RISC architectures had a lot more registers than the contemporary registers at the time. And if you could keep the operands in registers, that's much faster than keeping it in memory, which the older architectures, often the operands were kind of normally in memory, and they didn't have very many registers. So what John Hennessy was doing at Stanford, the MIPS is pronounced MIPS, for his MIPS project, He was he was very good at a compiler guy, and there had been a recent breakthrough in register allocations called graph coloring. So he kind of pushed the compiler to be able to keep operands in registers. Well, my project at Berkeley, I wasn't an expert in compilers, and I wasn't collaborating with a compiler expert. So we wanted to keep operands in registers, but we didn't have compiler experts. So we came upon this idea that we would have kind of a separate register for every procedure to make it easier to keep the operands in registers. And that's the windowing. So you call a procedure, you get a new set of registers. You call a procedure, you get new registers. And when you return, you get rid of that. So it has a lot more registers on the chip. But we did it in hardware to try and keep the operands in registers, what my friend Hennessy did using compilers. I mean, had we had compiler experts, we surely would have, we likely would have done it with the compiler, but we didn't have that. But a RISC architecture that doesn't keep operands in registers is not going to be a very effective one. So that's why we proceeded on that path.
Oh, that is very interesting, sir. Moving on, you have led the network of workstations project at UC Berkeley, which used the idea of cluster computing. Could you elaborate a bit on the project?
Yeah, it was with my colleagues, David Culler, Tom Anderson, and Eric Brewer. The four of us worked on it. So I had done a sabbatical in Boston at a supercomputer company called Thinking Machines. And while I was on sabbatical there, it just kind of struck me that they were using kind of standard microprocessors that in fact used the SPARC microprocessors, which were based on the Berkeley RISC efforts. So the SPARC microprocessors, and so they're putting hundreds or thousands of them together, and they'd have a custom network, and that was a supercomputer. And so kind of in the back of my mind, it says, well, and then they charge a lot of money for them, right? Supercomputers were very expensive. Well, kind of when I came back from sabbatical, kind of the question was, well, those microprocessors that were in the supercomputer, at kind of the building block of the supercomputer, were also in workstations. It was the same microprocessor in both places. Well, then what started to happen in the local area networks, basically the original kind of Ethernets were kind of buses, right? You'd share this cable and all of the computers on the network would share that one cable. So it didn't have a lot of bandwidth. But by the time that we were starting to work on the network and workstation problems in 1990, what had happened, there started to be switch-based local area networks. So there were switches which had a lot more bandwidth. And the question was, well, I wonder how good a supercomputer we could build using switch-based local area networks as the interconnect and put a lot of these together. And because the argument was, we thought it'd be a lot cheaper because the workstations are kind of commodities. They build millions of them a year. We just get, say, 100 of those together, and then we would try the switches that people were building for the local area networks. And then the question was, well, how much bandwidth was in the local area network? What was the latency of that local area network that was switched? And how good a computer could that be? So that was kind of the motivation for it, the supercomputer to be. Now, what turned out fortuitously for us, and at the same time this was happening, my friend at Stanford University, Hennessy, was leading a project that was called Flash. And that project was trying to also do a supercomputer. But they thought because software is hard to do in parallel computing, what was important was to have a cache coherent computer that could, at large scale, so that you could have, say, 100 or 200 processors in it, and everything would be cache coherent. So one processor modifies a location in memory, and all the other hundreds of other processors, if they access that data, would see the latest update. What we were doing with a network of workstations was that it was not cache coherent. It was just what we call today a cluster of them. So we were trying to do kind of supercomputer things like calculate LINPACK, or database things like doing sort. And Eric Brewer joined us, who is a young faculty member, and he looked at what we were doing and said, I think this collection of data would be great for internet services, that we could crawl the World Wide Web, and we could create a search engine out of your technology. Because the search engine doesn't really need to have cache coherent everywhere. It's not doing some kind of, computational fluid flow, dynamic fluid flow program that ran on some computer and porting it. We're writing it from scratch, and I think it'd be great for web services. Or for search as a search engine. It'd be fantastic for a search engine. So he had that idea with those other things. At the time, the leading search engine was called Alta Vista, and it was actually constructed from very large scale multiprocessors that would have, 64 or 128. They were very expensive. They'd use a few of those to do the search engine. And he thought this network of workstations would be much better technology to do that. And he was right. That basically that led to a search engine that is developed at Berkeley, and for a while that search engine was the best search engine around. And then he did a startup company that was based on it. That was called Inktomy. So this predated Google. Google came along later with better search technology, but they also decided to build their computing infrastructure out of kind of cluster technology, like the Network of Workstations project. So that was kind of the success of that project. So it started off with kind of the hypothesis: here's this new technology of switch-based local networks. How good a classical computer can we build it from it? But kind of the legacy was it kind of, sometimes people call it a capability. It allowed a new capability. It would allow us to build a search engine out of it, which much more economically, much more scalable. We built like 100 workstation with 100, but you could scale it up to 1,000. And what was very important for search technology is to scale it up so you could handle it. As more and more people started using the World Wide Web and searching, you needed computing that could easily scale to giant size. That was much more important than cache coherence. So there were kind of these two rival projects at Berkeley and Stanford, something like the RISC effort and the MIPS effort, that had different architecture bets. This was kind of a bigger difference architecture bets. And I think the way it turned out historically is clusters basically won that. There's a bunch of interesting ideas that were explored with the Flash projects, but that they have played a smaller commercial role than clusters have. And today everything, all of the World Wide Web runs in clusters with amazing scale. To 50,000 computers and clusters and stuff like that. So I think that's that story.
Yes, sir. Like, it's remarkable how technology has advanced so far. That was really interesting. Now, there are a myriad of issues beyond performance that impact computer architecture. What are the other factors influencing computer architecture, and what sort of impact the non-performance metrics have on the architecture?
Yeah, I think computing has always been cost performance. I've been, since I still work at Berkeley a day a week, but for 4 days a week I work at Google. And I get to see firsthand the industrial perspective. So I think from the industrial perspective, it's performance, and the cost part of it is a little bit different. It's not just what it costs to buy it, it's what it costs to buy it and to own it. So that's called total cost of ownership. So from a Google perspective, what they care about is performance is the numerator, and the divider is the total cost of ownership. So what goes into total cost of ownership is the cost of purchasing, but then the cost of using, which has to do with cooling it and supplying electricity to it and how much electricity it uses. So from this industrial perspective, you want to get the best performance, and the cost of purchase as well as the cost of operation. So electricity usage is important, just kind of from a dollars and cents perspective. There's also this, we're the planet is worried about global climate change. We're worried about energy usage. I've been involved recently in looking at the use of machine learning and its impact on energy use and carbon footprint. So I think a second issue is not only just from a cost performance perspective, worry about energy use, but also from kind of being responsible, members of humanity and trying to build computers that are more energy efficient. So I think the energy efficiency is a non-performance one. And then the other one that's increasingly disturbing is security. The fact that we've built this amazing technology that's incredibly fast and incredibly cheap, but it's not very secure. We're constantly reading stories about people breaking in and hoodwinking people or scamming them and getting their money. It's really terrible that it's this bad. I think people hoped maybe we'd figure out a way to make software more dependable, and that would address the security issues, but that has proven not to be the case. So I think if we're really going to make progress on security, we're going to need advances in hardware to try and tackle it. We're going to have to accept buggy software running on our hardware and still offer security. So I think security is another really important non-performance issue for us to look at, and it's kind of a wide open area, I think. And then the one after that would be reliability. There's been a really interesting article by David Culler, who is my colleague at Berkeley, and he's also started to work for Google, kind of following in my footsteps. He retired and did that. And he recently did a paper that it was the Hot OS conference that's called Silent Data Corruption. And computers today have error correcting systems that are trying to catch random errors and then correct them, or at least let the computer know that errors happen. So he wrote this paper on silent data corruption, and it's called silent because it makes errors and people don't know it. And I think the title of the paper is Cores That Can't Count, is the title of the paper. So it's a fairly provocative story of real industrial machines where it's making mistakes and you don't know about it, which is kind of a scary new ground. So this kind of dependability story, reliability story, and it could be, as we're getting down to Moore's law and finer technologies and high clock rates and all of that, we're starting to run into some problems there. So that's another area that's non-performance that's going to be important. It used to be that hardware was always reliable, and if there were bugs, it was because there's bugs in the software that ran on it. But as this paper points out, we're starting to see real world problems in the dependability of the hardware, and it's certainly something that we would like to fix. I think that paper talks about maybe software mechanisms where you'd have software checking to check against, make sure you're not having silent data corruption. But that's another area. So I would say, the performance for total cost of ownership, that's kind of a long-standing, maybe slightly more sophisticated than cost performance ones. But then energy use, security, and now dependability, a problem that is relatively new, or the awareness of it is relatively new.
Yes, sir. You had talked about Moore's law in the previous answer, but we had already seen Moore's law failing and the breakdown of Lennard scaling. What, in your opinion, are the major roadblocks that the computer architecture community is facing currently, and what is the research being pursued in the direction to tackle the same? Should we be expecting a breakthrough in the same direction?
Yeah, what John and I did in our Turing Award accept speech, and then we got turned into a paper. I think it's called a golden age for computer architecture or something like that. What we said, as far as we can tell, the way we're going to make progress, given that the transistors aren't that much better, is that we're going to have to be much more innovative in computer architecture. And one way to do that is to build what we call domain-specific architectures, that a processor that only tries to work well in one domain. The general-purpose microprocessor, for decades, the goal was you make that faster, and it's the tide that lifts all boats. Everybody's program goes faster, and for decades that was true. We would double performance every 18 months, and so everybody's program got faster in the whole world. That was great. Going forward, we don't think that's possible. The one interesting thing that's happened, since we published the paper, has been instead of in the past with Moore's law was like how many transistors you can put on the chip, and that was two factors. That was the transistors getting smaller and the chips getting bigger. And practically speaking, he was talking about a single chip design, and for decades, that's what dominated design. The chip, almost always, what was the microprocessor was one chip because that was the easiest way to integrate it. What's happened recently with the slowdown of Moore's law and Dennard scaling ending is a move to what's called chiplets. And so AMD, for the last couple of years, and recently Intel, have switched instead of one big chip, that could be that big, would construct out of lots of small chips and then assemble them together on some kind of package. Now, so why did they do that? Well, by doing it from small chips, the yield would be better. So as if you read in our textbook, the smaller the chip, the more likely it's going to work. So you can fit, only this, the wafer is kind of this big in diameter. How many chips can you fit on? Well, if the chips are this big, you can't fit very many of them on, and they're much more likely to have a flaw. If they're little tiny ones, you fit a lot more on it, and the chances of that one having a flaw are much less. So one argument for chiplets was to get it, bring the price down because the yield would be much higher in the smaller chips. Another argument is you could actually have more silicon there. There's a limit to the maximum size chip you can build in any generation. It's called the maximum reticle size. So, but if you do it out of chiplets, you could have more transistors in the chiplets than you could fit in the biggest chip you could make. So that's another reason. So both of the companies are going that way. And people are arguing if you make it out of chiplets and you use clever packaging, then you can put as many transistors as you want. So Moore's law is still alive, but that's not what Moore was talking about. But we will be able to get bigger systems out of chiplets. What they're doing primarily is putting these packages together is giving you a lot more cores. So today it was, say a chip might have 28 cores or 32 cores. The recent AMD chip has, out of 8 chiplets, total has 64 cores in it, and they have plans for the future for 96 cores. So tremendously more cores. So if your software can take advantage of a lot of cores in one chip, then you're in pretty good shape. However, a lot of software will be bottlenecked by something else on the chip, won't be able to take advantage of all those cores. And if that's true for your applications, then that's not going to help so much. So we think the path is specialization. So either it'll be specialization like only on a particular domain, or it'll be specialization of aiming for some other class of programs that don't run well on these high core count machines. And so, but the basic idea is let's get away from the single general purpose computer. We'll have more different types of ways to do that. Some of them will have special units that work for some classes of applications. Some of them may be just different balances of memory bandwidth and processors and things like that. So I think as far as we can tell, the past is going to be much more homogeneous than the future is going to be in terms of hardware.
That is very interesting, sir. I hope the viewers are pleased to hear that. Moving on to the next question. What is your opinion on the need for open source instruction set architecture?
Yeah. So one of the really exciting things, so you introduced it as RISC-V. It actually is a Roman numeral, so it's RISC-V. So at Berkeley in 2010, we're doing a research project in the area of parallel computer architecture, and my colleagues, Krista Sanovich and 2 graduate students, said, well, if we're going to build hardware, we need an instruction set. And even though Intel is one of the sponsors, we can't use the x86 because it's incredibly complicated. It'd be hard to get our work done. And plus, Intel doesn't want you to do it. Intel owns it. The other obvious one was ARM, but same thing, right? ARM, well, it's not that complicated, but ARM owns it, and it absolutely, ARM doesn't want, you can't use it without a license. So we needed to do our own, so we did. We built our own RISC instruction set in kind of a brand new one. The ones that I worked on, we did 4 of them in the 1980s, and then we moved on and did the RAID project and then the network architecture project. So kind of, there were 4 RISC projects in the 1980s, and they had 4 different names on it. So I was actually at a event for Turing Award winners. I had not won the Turing Award winners, but they were there, and I got to talk to Nicholas Vert, the person who developed Pascal, and he developed a whole sequence of really interesting languages. I can't think of them all, but each of them had a different name. And he told me, I have one regret, and I wish I'd called them Pascal 1, Pascal 2, Pascal 3, and Pascal 4. That was a mistake. He said, that's funny when he said that, because I thought about that too. I don't much think about it. I wished I'd called the projects at Berkeley RISC-1, RISC-2, RISC-3, RISC-4. So I told that to the people there. So they said, all right, if we're going to do a brand new RISC instruction set in 2010, let's call it RISC-V, paying homage to the ones from the 1980s. We'll call this one RISC-V. So that, but it'll benefit from 20 years of hindsight or 30 years of hindsight, right? We'll see what they did wrong, we'll make it right. So we built a very nice, clean RISC instruction set for our use at Berkeley in the classroom and in our research. And we thought that other academics would use it. We thought other researchers would be in our same quandary, come to the same conclusion, and we would share that. That was our idea. So we made that open source. And we started building chips and taught it in our courses and all that stuff, but hardly anybody else used it. There weren't other academics. We were surprised that other academics didn't, but they didn't. But then about 4 years into it, we started getting questions from India. It's like, what, your instruction set that you used in your class in the fall, in the spring you changed it. Why did you change it? We always get all kinds of questions from outsiders. So, this is the reasons we changed it, but why do you care? This is for our use, nobody else is using it. And then they said, well, we are interested in having an open instruction set that we could use for our purposes too. And we learned about yours and it looks pretty good. Well, once we heard of the idea that there was interest in, the 2010s in an open instruction set, well, we thought that was a great idea. And if RISC-V could be helpful there, we wanted to make that happen. So once we talked to people like the Shakti Project India and a couple of others, that there was, a real palpable interest of a viable open source instruction set. Well, then, Chris Hasanovich and I thought, boy, let's try and make that happen. So imitating things like Linux that had the Linux Foundation, we helped start a foundation to manage the RISC-V and try to sign people up to use it. And that's been going on now. I think the foundation started about 2015, and this is 2022. And the foundation is really large and popular. And there's billions now, billions of RISC-V cores are shipped now. I would say today, the two most important instruction sets are still x86 and ARM, but now the third one is probably RISC-V in terms of popularity and buy-in and things like that. So I think the idea, and we've been doing this a while and talked to a bunch of people who are lots of people are very excited about it, and kind of asked them why. We did a kind of a 10-year anniversary, so we interviewed people. So, well, why are you so excited about this? And there's a few people kind of laid out that they saw that it would be possible, technically possible, to have a universal instruction set that could be used for anything. If we had a 32-bit one and a 64-bit one, we could use it from everything, things like to go on my watch, to things in supercomputers, in the cloud, and clusters, everywhere. We could have a common instruction set. And said, technically, we could do that. The business reasons might be difficult, but technically it would be possible. And if we're going to have a common instruction set, it should be open source. If you think of it like a lingua franca, if English is the current lingua franca, if it was proprietary and we had to pay somebody in England money for every word we use, that wouldn't work. We can't have a proprietary lingua franca. So the same thing, I think, is in computing. The excitement of a lingua franca, everybody could use everywhere, a common instruction set, everybody could learn, everybody could write software for, and that we'd all develop it together. It'd be a worldwide project to be able to do that. Is an exciting vision. And so I think that's part of the enthusiasm and why RISC-V is so popular. And I think there's a real chance that 5 years from now, 10 years from now, RISC-V could be, the most important instruction set, or the second most important instruction set. If you think Linux is kind of our example, 20 years ago or 25 years ago, it seemed like kind of a toy operating system. Then IBM and others endorsed it, and it became more serious. and now it's probably the dominant operating system. There still are proprietary operating systems, but probably most of the use is Linux. So that's possible that this would happen, that RISC-V could eventually become the dominant instruction set. That doesn't mean the other ones will all go away. There's still the IBM 360 instruction set is 60 years old almost, and it still has its own niche that it's very successful at. So it wouldn't be everybody uses it for everything, but it can become very popular, and that's a very exciting possibility. And I like the idea of this kind of worldwide collaboration around building and developing the instruction set and processors and stuff like that. It's kind of it just as the lingua franca of the universal instruction set. It's pleasing to think that hardware people could get together and collaborate around the world, just like software people have done for many years.
That was very informative, sir. Thank you for that. Now we have a representative from MTX Incorporated who would like to ask Dr. Patterson a couple of questions as a part of the fireside chat. MTX Group Incorporated is a global technology consulting firm powered from the MAVQ AI platform. MTX improves decision making for organizations with speed and quality by leveraging MAVQ and partnering with other leading cloud technologies such as Amazon Web Services, Google Cloud, and Salesforce. With innovation and service at the core of MTX's DNA, the company helps transform organizations' long term strategy with outcomes in mind surrounding happiness, health, and the economy. MAVQ is a low-code platform with a native AI capabilities that enables organizations to build fast, cohesive, and user-friendly applications to digitally transform while creating valuable insights and outcomes. In the past year, MTX grew exponentially, expanding from 300 to now over 1,300 family members worldwide. MTX is headquartered in Frisco, Texas, with corporate offices in Hyderabad, Jaipur, the United States, Canada, and Australia. Globally, MTX delivers public sector solutions and transformation projects in healthcare, emergency services, workforce development, public safety, education, transportation, and cybersecurity. Today, we have with us Mr. Sumit Kurana, program lead at MAVQ from MTX, who would like to ask a couple of questions. Over to you, sir.
Thank you, Ritwin, for the introduction. And first of all, very good evening, Mr. David. It has been very insightful, all the answers that and all the questions that you have answered, right? It is really insightful. I would also like to ask a couple of questions from my side.
Sure.
Thank you for the opportunity. The first one would be like in today's world, right? Technology has been present in almost every aspect of our lives, right? It impacts us everywhere. So, as we make our lives easier through more advanced innovations, technologies, do you think is there a way or is there a point that we should draw a line, so that it does not impact the humanity in a negative way?
Well, yeah, I think one of the questions about advances in science and engineering is what are the upsides and downsides of the advances? I think in biology, I think they do a better job of worrying about the downsides of technology than we do in the computer science, at least. In biology, they actually, when some technology comes along, they potentially have very negative downsides. They'll pause what they're doing and get together as a group and decide what they want to do. So a recent example is the CRISPR technology that was developed in, Berkeley played a very big role in the CRISPR technology that does gene editing. And the question was, what should we allow gene editing to be done on humans and human babies? And they all agreed, nope, that can't be done, shouldn't be done. And then they set policies like that. There have been some other things in biology where they've done that. And so they worried about the negatives of technologies and tried to, ban that kind of research. There was a person in China who violated that ban, but fortunately, the government, cracked down on that. And so I think so far, the ban, but at least they pause and do that. I don't think that's been our tradition in computer science. We've been building technology that's definitely got upsides and haven't as much in advance, at least, worried about the downsides. Now, if particularly in machine learning, the kind of the technology was developed, and then there became clearly issues about fairness and that were worrisome. And so I think after it became an issue, then people started working on it. It's tough to draw a line. Biology, I guess, has this tradition of getting together, and the leaders get together and they set some lines about you can't cross. That's kind of rare, right? We don't normally see that unless it has very obvious negative impact on people. The stuff that we do doesn't have obvious negative impacts, like facial recognition, right? There's a lot of positive benefits. I use it on my phone, right? Outside of the phone, it's clearly there's upsides there. There's also downsides of facial recognition. Governments could use it to find people, just look for people or to monitor people, right? So it's hard to it's certainly hard to say, well, don't develop this new thing because it has negatives, because almost everything has some negatives. I think, maybe I would say going forward, I've thought about some compared to, I've talked about my undergraduate days, which were many decades ago. I would say today, going forward, our technology has so much impact. It's so widely divorced that I think undergraduates interested in computing should take a course in ethics, because I think it's entirely plausible these days, sometimes in your career, you're going to be asked to do something that you're going to feel uncomfortable with. And, you'll be faced with, should I do that? Or should I, resign, right? I should go find another job because I don't want to do that. There's been hyperscaler companies that have made the headlines on things that they've done that have had really bad things to do with society. I would say, without naming names, at least one of them knew the downsides of what they were doing and decided profits was more important than the negative impact, right? And for that company, there was somebody who worked there who said, I don't feel comfortable with this. I'm going to collect information and reveal what the company's doing. So I think there's this, but there are lots of people, I was, obviously, I guess I was talking about Facebook. There were, I don't know, tens of thousands of people who work for Facebook. Only one person did this, right? What did the other, there must have been other people who knew about that, and they chose not to go forward, right? They chose, maybe some of them quit, maybe that's it. I know people who, I don't think they knew about this level of detail, but several years ago decided I don't feel comfortable working here and I'm going to go work someplace else. But I think this might be something going forward that students right now should think about, maybe take a course in ethics, and possibly at some time they're going to have to make this decision. I would say, what I can tell you is once you're as old as I am and you look back on your career, you're going to feel a lot. It's going to be pretty important if you face some of these ethical decisions that you made the right choice, to feel good about what you did. At the time, it'd be hard to stop and get a new job, but I think you would, later in your life, you'd be really glad you had to do something like that. So I think, how do we prescribe what computers can do and can't do? That's really, really hard, because so often, usually there's so much upside as well as some downside that it's hard to say that you can't do that. But I think we should start being more careful, thinking about some individual things that we might be asked to do, about whether that crosses the line and whether we should be comfortable with it.
Definitely, Mr. David. Yes, it also boils down. I agree, right? It also boils down to the individuals as well, right?
Yeah.
Yes.
So I think you could just say, it's the leaders of the company made the decision. It's not up to me. I don't think that's a very satisfactory answer. I think there'll be situations. Well, I think in the past it would be maybe not so crisp and clear about that. But I think our technology is so pervasive now. I think it'll be pretty clear. I won't be one of those things like, wow, I wish I'd thought about that 10 years ago. I didn't realize how bad it would be. I think it's going to be pretty clear when you could be asked to do something that, probably you wouldn't want to tell your mom that you did this, right? It's going to be pretty clear that this isn't something that people are you're going to want to brag about. And if you're doing stuff you don't want to brag about, life is kind of too short for that. You should be finding something else to do that you can brag about.
Definitely. Yes. Thank you, Mr. David. I'll proceed with my another question. So there are two new fields which are emerging, right? We have been calling about AI for systems and systems for AI, right? So what do you think about these fields, and what major breakthroughs, would these fields help us in, right? Is there any particular focus areas or any problems that they should focus or the researchers should focus on while working on these?
Yeah, so I think, this will be another long answer. So I think in my career, I've seen a few kind of transformative technologies. One of them was the microprocessor pretty early in my career. Once you could put a whole computer on a chip, that was an empowering technology. It led to personal computers in cars, all kinds of things. Another one was the internet, right? That was incredibly transformative, changed the world. Probably smartphones fit in that, that kind of the accessibility, the functions that could have, that's probably there. And whether we'd separate the World Wide Web from the internet, maybe that things. And so the question was for me for about the last 5 years since I've been working at Google, is machine learning one of those things? Is that a transformative thing, or is it just a little bump? But I've been asking that question for 5 years, and it keeps getting more impactful. So I think probably machine learning is one of these transformative technologies. So we call it AI, but kind of as I've learned, there's AI is kind of this big bubble, the big circle that's been around for a long time, and within AI, and AI is kind of this top-down approach. If we write all the rules down, intelligence will world. Inside that was kind of a minority community that didn't agree with the rest of the world and said, humans will never be able to write down all the rules. We have to learn the rules from data, that we'll look at data and figure out the rules. So it's easier to discover the rules of intelligence than to write them down. And then within the machine learning community, there's a smaller group that said, yeah, we have to learn from data, but the way to do that is with neural networks. That we will give it labeled data, it will learn from labeled data, we'll train it, and that's going to work. And what's happened over the last decade is it wasn't AI that won, and it wasn't general machine learning won, it was the deep neural networking that won. And the people who got the Turing Award the year after John and I, Bengio and Hinton and LeCun, they were people who championed the deep learning, and that is in recognition of the impact it's had. So I think machine learning is this transformative technology. And typically what it does, it'll move into an area like, say, computer vision, where they had all of these algorithms that they used for years, and they got replaced by very simple algorithms. That's not a lot of code, and you just give it millions of examples that are labeled, and it trains it. And they threw away all that old code and replaced it by simple code and a lot of data and a lot of machine cycles. So that's, transformed some of these kind of like signal processing applications like computer vision and language processing and stuff like that. So when you talk about AI for systems, you're talking about deep neural networking for systems. So that could well happen in our field where we're replacing things that have always been written. We write millions of lines of code, and instead it'll be something much simpler where the smarts come from training it from data. So that would be really interesting where we find examples of that. At Google, they've done some work on some computer-aided design things like place and route, and they've had some success at that. I think some other things like in verification testing, they've done that. So there's been examples in terms of the AI systems of this deep neural networking attacking some of these classic problems there. And kind of the question will be, how far will that go? There's been work in database systems where they found better data structures by looking at the data. Will it affect compilers? Compilers are doing this kind of language translation. Can machine learning play a role there? So I don't know quite how far it's going to go. So that was the AI for systems. In terms of systems for AI, that's actually what I've been working on in the last 5 years. And Google's been working on this for 10 years or so, is building hardware in particular to make machine learning go faster. So That's been very exciting. This is going back to what I talked about earlier, domain-specific architecture. Here, the domain is machine learning, and Moore's law is slowing down just when we need more cycles. Machine learning, the first word in machine learning is machines. It needs a lot of machines. So it's using a lot of cycles, and instead of Moore's law delivering those cycles, it's not. So we're doing it via specialization. And we're doing that. Amazon's doing it. Alibaba is doing it. Even the NVIDIA GPUs are being specialized. GPU stands for graphics, but they're being optimized for machine learning so that they can run machine learning better. There's a lot of innovation there. So a lot of hardware innovation in terms of systems for AI to accelerate it. And it's helping. We talked about this earlier, responsibilities about energy efficiency. We're going to do a blog next month, February 15th, where we'll talk about how the hardware that Google has built has reduced kept our energy use at a relatively low level. And you have to wait for the blog on February 15th, but it's helped reduce our energy costs. It's helped advance make advances in machine learning by running programs much faster. So in terms of system AI, particularly computer architecture, that's been a big deal. There's been programming languages, there's compiler technology. So there's been a lot of systems that have helped the machine learning deep neural networking be much faster, more efficient. So yeah, I think both of those have been really interesting.
Thank you, Mr. David, and I am really looking forward to the blog on 15th of February. Right, I'll look forward to that.
Yeah, it'll be under my name, but I think it'll be easy to find.
Yep, sure, definitely yes. I have one last question for you, Mr. David. So with Google's new Tensor chip, right, coming, that we have, do you think that the complex AI algorithms like text to speech or facial recognition that we just talked about, right, and other algorithms as well, will need to shift away from cloud computing to offline? And should companies be prepared?
Well, the way this deep neural network works, there's two phases, right? There's the learning part, which is called training, and then after you have a trained model, you've shown it millions of images and it can recognize things. Then the second phase gets called inference or serving. Sometimes it's kind of its development, and then you're using it in production. So unquestionably, in terms of delivering it, providing intelligence, I've got an Apple Watch here, in your phone or in your cell phone, that's an example of inference. So that's on the edge, not in the data center. There are things that are served, or inference does run in the data center, but it also absolutely runs on phones and edges. Training, on the other hand, is almost always done in the data center. We're talking about, lots of data, running for weeks on lots of computers. So right now, at the cloud or the data center, absolutely dominates the training phase of it. There's a little bit of work that's done called distributed learning, where you run it on phones and watches. The benefit, that has a benefit of privacy. The data doesn't leave the device, so that's a positive. But it does. These processors aren't that fast. They don't have that much memory. So training would be, there's an argument for it, but if you don't have, say, privacy issues, it's much easier, much faster to do things in the cloud. So that's where most of it's going to be done. I don't see that changing very quickly in terms of the training. Inference on the edge makes tremendous sense for, there's slower latency. There's a lot of reasons for it to be, the inference phase to be on the edge.
Thanks, Mr. David. Thank you so much for answering these questions.
Hello, I'll be taking over now. Thank you, sir, for the questions. So moving on to the final couple of questions. IIT Madras's in-house Shakti processor program, which started as an academic initiative by the RISC group back in 2014, has made significant developments in developing open source production grade processors. What is your opinion on such open source design initiatives, and moving forward, how important do you think they are?
Yeah, I think that's, first of all, it's very exciting. I think from an academic perspective, I always thought it was interesting that if you study compilers or you study operating systems, you can see the code of industrial strength designs. You can, because people are running LLVM and GCC for compilers in Linux. If you're a student, you can see what the code looks like. Well, before, when things are proprietary, you can read stuff in books, and you can, you have to believe the books say this is how they do things, but you don't really know, right? But I thought it was very cool that you can go in and see what's going on. And not only can you see, you can actually make changes to it and improve it, and people can see what you do. So it was much more inclusive and participatory. So that's what I like about doing that in hardware, with open source hardware, is you can see designs like examples are like Western Digital, that there's kind of two big disk makers left, and Western Digital is one of the two. They have made their design, their proprietary design, that they're shipping in. Either they are shipping in every disk drive, or they will. You can see what's in there. You can look at the code, the Verilog code itself, and see it yourself. And you could even download it and run it on your own design. So the fact that companies are doing industrial strength designs and then donating for people to use is very, is very exciting. It's much more inclusive and accessible. You can go see what's going on. You don't have to believe what the textbook says. You don't have to believe what your professor. You can go read it. You can go see the stuff yourself and see how industrial strengths are designed. So I think that's, from an educational perspective, it's very exciting. In terms of the industrial impact, I think we're going to have to see. There's certainly some open source designs that I think are pretty popular. I think the ones done at ETH, I'm assuming that the Shakti processors will be popular in India. Indian industry will use them, but it's not. I don't know yet whether, because there's also companies that are making them commercially, and one of the benefits of getting one from a company commercially, even though they charge money, they provide support. They'll maintain it. So if you get the design and you put it in your chip and something doesn't work, there's somebody you can go to complain to, right? Because, hey, I paid for this thing, it doesn't work. If you do an open source design, there's no guarantees there. So it'll be interesting to see how that plays out. I don't, even though I'm on the board, I don't really have an idea of how popular the proprietary RISC-V designs are versus the open source ones. So what the kind of the industrial impact of these open source designs it'll be interesting to see. I'm pretty sure at least some of them are widely used, but we'll see what happens over the years. But the fact that some can be open, is there be viable open ones, is what's exciting. So for example, when I talked about security, one of the hard things in security is, how do you test it? Well, to me, if I had to do that, I would try and come up, if I had a hardware idea, I would take one of these open source designs, put my idea into it, put software in it, and connect it to the internet and see if people can break in, right? We could make security experimental. But for that to happen, I have to have access. I need an open instruction set so I can have open implementations, so I can modify them with my idea and run software on it and see how well it works. And of course, with modern FPGAs, they're slower, but if you were using it over the internet, it can run some number of users. So you could have a really industrial strength design with your innovation. You have a software stack that you can port and make changes to it. So it makes it much more accessible for people who want to do more realistic, innovative work, and even something that potentially, if you did it in an open source design, people might just pick it up and use it. So it kind of, I think it multiplies the importance of computer architecture research, the fact that they're open designs that can accept them, just like I think that's been true in compilers and operating systems. You can have an idea, show people how to use it, and it could get adopted by the open source designs where you're never quite sure what the proprietors in. So I think it's a real boon to computer architecture. The open instruction set itself is a boon to industry. As when we were talking to people early on, if you're a startup company and you want to build hardware, well, one of the first things, without open architectures, what you have to do is do a contract with a company that you want to license the design from. And so that takes time and money to negotiate the contract, because you have to You want to make sure not to pay ridiculous royalty rates and stuff like that. So it's a careful negotiation that takes a long time. And that's one of the first things you have to do. But with RISC-V, you can just say, okay, I'm picking RISC-V. Somebody's going to give me the processor, whether it's open source, or I'm going to go to sci-fi or to Andes or some other commercial funder. Yeah, I'll figure that out later, but we're going with RISC-V. And so that, number one, saves a lot of time. It also saves money, but I think the big thing is it saves time. So I think, particularly for startups, the open architecture is going to be a big deal, as well as for academia. It's going to be getting much more realism in the classroom is available because of the open designs. So I think it's very exciting, as well as this vision of having a universal instruction set that everybody uses. So I think we're on that path. You know, it takes a while to know. I don't think we can declare victory yet. So far, all the signs are positive, but you know, we'll see. What's it like? You know, hopefully you can invite me back in 5 years, and we'll see how it looks then.
Yes, sir, we surely hope so. That indeed is very interesting. We do hope such open source design initiatives come forward. Finally, what is your advice to the students who would be watching this session who are keen on pursuing a research career in the field of computer architecture to bring about a difference?
You know, I would say these days, just to keep in mind, like I said, I was the first to go to college in my family, first to graduate from college. My dad started college, but didn't quite graduate. It took him a long time. But I went and got a PhD. These days in computer architecture, a lot of people have PhDs. Now, it takes a long time to get a PhD, and especially when you've been in school for a long time and you're 21 or 22, it's getting out and making money seems like a great idea. But I would say if you do have the possibility of going and get a PhD, you should seriously think about it. One of the things I found when I retired was I went to a retirement thing, and I had been thinking, you know, based on people I know, if I could live to my 80s, I should be happy. But the person who gave the talk there said, you know, the number one correlation with longevity is education. So for the people in this room who are retiring from professors from UC Berkeley, you guys are going to live a long time. And so as a result of that talk, I raised my expectations by another decade. So I thought I have another decade. And as I looked at the data, I think she's right. And what she said, for younger people, like people like you guys are going to live to 100. So if you're going to live to 100, you know, you could have plenty of retirement time. And another 5 years of school, if instead of going in the workforce at 21, you go in at 26 or so. That's in the big picture, that's not that long. So I think if you want to do computer architecture, you should seriously think about going to grad school. There's a lot of stuff to learn. A lot of the people who are leaders in computer architectures do have PhDs. I know Google, one of the reasons I did a sabbatical at Google was just like, why are they hiring all these PhDs? And kind of the Google version of it is, well, we can hire people who have this really great training, can write and speak, and they feel comfortable dealing with issues where the answer isn't very clear. You know, there's a lot of, it's not clear what the right thing to do is, to go look at that, kind of do the research, figure it out, and solve it. Those are pretty useful people, even though they're not, you know, after they get to Google, they're not writing lots of papers. They're just innovating in time. So I think I would say that's kind of what I would say if you're interested in this area, is to seriously think about going to graduate school, getting certainly a master's degree or a PhD. Other things in terms of preparing yourself, taking a wide variety of courses, computer architecture, you know, it's a hardware software boundary. This machine learning stuff, it's actually, or domain specific architecture, you need to learn domains. So taking advantage of being in a university where people try to teach you things, they try to make it easy to learn, because once you leave the university, you have to learn it on your own. It's probably easier at the university. So I'd seriously think about, you know, taking as many courses as you can, do that. Beyond that, you know, get some real world experience. There are people in computer architecture who don't feel comfortable building hardware. I've always found that a little unusual, but, you know, make sure that hardware doesn't scare you, that you take courses, you could do that. Certainly ought to be able to build things in FPGAs and stuff like that. And then, machine learning is this, like, I think it's one of these transformative technologies. You should learn about that as well as the classic computer science stuff. And then there's a real excitement about hardware. There's something inspiring about building a chip and seeing it work. It's physical. It's there. That's this kind of like Christmas surprise, right? It goes away for months and it comes back, and you open it and what's going to happen, right? And it's very exciting to see it work. So it's got a kind of a interesting. I always thought in computer science the two really fun things to do is invent your own programming language, which is fun. It's the practical benefit. Not very many people get to invent a programming language and have people use it. And build your own computer. So if you can build your own programming language and build your own computer, that's a pretty intellectually exciting thing to do. For the hardware stuff, this is not such a crazy idea. These days, it's getting very economical to build a computer. There are, we're going to probably help foster a contest where people can come up with designs, and the top designs will get fabricated. It's getting cheaper to build hardware than older technologies. The FPGAs make it more realistic. So you really can build a computer yourself. You can build hardware, and we need some more innovations there. So so I think those are many of the things, and I think in computer architecture, or kind of in computer systems in general, it's important to know the literature. There's a bunch of ideas that have been in the TPUs that have been done at Google that are older ideas. Systolic arrays is an idea that goes back to the 1980s that had hardly been used at all since the 1980s and never used much commercially. But that's at the heart of the TPUs that Google is doing. So, you should be well read on, the important research of the past, even things that weren't necessarily successful if they were very interesting ideas that whose time wasn't right. So I think that's a lot of advice to give, but there you go.
Thank you, sir. I'm sure that the viewers are truly inspired by that. It was really inspiring and insightful to chat with you today. We believe that the audience would have enjoyed every minute of it. Once again, I take pleasure in thanking you for your presence today. We also thank our viewers, and we hope that you have had a memorable experience. Please fill the feedback form shared in the YouTube chat, which will help us improve in the upcoming sessions. Coming up next, we have Dr. Massimo Banzi's fireside chat at 1 p.m. and Honorable Justice R.C. Lahoti's lecture chat at 3 p.m. Stay tuned to Shaastra IIT Madras's YouTube channel for such inspiring and engaging sessions. Thank you.
Okay, thank you.
Thank you, sir.